Welcome to the Deep Dive, the show where we really get into the weeds on your technical challenges and hopefully help you find some mastery. Today, we are zeroing in on a really specific and super common problem that plagues anyone trying to seriously run a classic Tamiya buggy. We're talking the Grasshopper II, the Super Hornet, even the Rising Fighter. So your mission, should you choose to accept it, is not just about fixing a broken piece. Oh no. It's about engineering a permanent, high-performance solution. We're tackling that infamous front suspension failure. You know, the one happens the moment you try any kind of aggressive off-road driving, what everyone calls bashing. We want durability, yes, but also performance, real handling.
Yeah, and it's a critical mission because this isn't just a random part breaking. It's baked into the design. It's systemic. The stock setup, well, it's pretty much guaranteed to pop apart under heavy loads. And that's down to, really, two things. A material weakness in the key retainer, and maybe even more critical, some, let's say, fundamental geometric flaws from that original 80s design.
Okay, let's unpack that design flaw first, the actual mechanical failure point. Looking at the manual, you've got parts A5 and A6, right? The left and right swing arms.
Exactly. Those single arms, they move up and down, but they pivot on these little plastic nubs that sit in shallow recesses right there in the main ABS chassis tub. And the key part, the only part holding those nubs down, is part A1. It's this integrated brace and retainer piece. It kind of caps the whole assembly, and it's just held on with 3 BA5 tapping screws.
Right, so A1 is basically the gatekeeper, stops the arms lifting vertically and popping out. But, I mean, if it's screwed down tight, how does the arm manage to just jump out?
It really comes down to the material itself. That stock ABS plastic Tamiya used for the A1 part. Think about a hard landing or, smacking a curb. All that force shoots up the suspension arm and it pushes outwards and upwards on that little pivot nub. It's trying to pry the arm out of its socket, basically. Now, because those tapping screws only have shallow threads in the plastic tub and the A1 part itself is quite flexible, well, the whole thing just momentarily distorts under sharp impact. That ABS plastic of A1, it literally flexes open for a split second, like a tiny, weak spring, creating just enough of a gap for that pivot nub on the arm to escape. Arm pops out, boom, that side of the suspension collapses.
Huh. And the funny thing is, that failure, it was kind of acceptable back when these kits first came out, wasn't it?
Absolutely. You gotta have context. This design, it was simple. It worked fine for what the car was meant to do back then. Light running, maybe the smaller 380 size motor, old NiCad batteries.
Right.
But the second you drop in a modern LiPo pack and a decent brushless motor, standard stuff for bashing, now you're putting forces through it that are, exponentially higher than that original plastic was ever meant to see.
So if part A1 is the Achilles heel, the obvious thought is, fix the material, right?
Yeah.
Why not just, epoxy part A1 to the chassis, make it super rigid so the arms can never lift? Problem solved. Max durability.
That's a tempting thought, but it'd be a mistake. A big one, actually. Because you'd just be reinforcing a flawed system, a system that actively causes the stress that breaks the part in the first place. And this is where it gets, really interesting. The weak plastic, that's only half the equation. The underlying geometry, the way that single swing arm is set up, that's the other deeper issue.
Okay, the vicious cycle you mentioned earlier. So tell us about these dynamic flaws that make the buggy so unstable, it basically crashes itself until something breaks.
Okay, flaw number 1 is bump steer. And it's pretty bad on these. The way the single suspension arm and the steering tie rod are laid out, they just don't move together correctly. They travel in different non-parallel arcs as the suspension compresses and extends.
And what does that actually feel like when you're driving it? How does that manifest?
It feels unpredictable, twitchy, nervous. Every single time you hit a bump, which is exactly what these buggies are supposed to handle, the front wheel's toe angle changes sharply. So instead of tracking straight, the wheel literally steers itself left or right. Even if you're holding the transmitter perfectly still, you're constantly fighting it, correcting it. It leads to losing control, especially going fast.
Okay, so that's bump steer. What's the second flaw?
The second one is often called, maybe a bit dramatically, tragic camber game. So camber is the tilt of the wheel, top in or top out. With the single swing arm design, as the arm moves up through its travel, that wheel's camber angle changes a lot. When the suspension compresses hard, like in a corner or on landing, the wheel ends up tilting way inwards at the top.
Right, which must kill the grip, doesn't it? Reducing the contact patch.
Precisely. Massively reduces it. So you're trying to corner hard, the suspension loads up, the wheel tilts excessively, and suddenly the amount of rubber actually touching the dirt shrinks right down. Less contact patch means less grip. Less grip means the buggy is super prone to flipping over, spinning out, or just washing out wide in the turn.
Okay, let me connect the dots here. So the geometry itself makes the buggy inherently unstable, prone to crashing and flipping.
Huh.
And those frequent high-impact crashes then directly exploit the material weakness in that flexible A1 retainer, causing the suspension arm to pop out.
You got it. It's a perfect storm. The geometry makes you crash, and the weak plastic ensures something breaks when you do. A truly vicious cycle.
Right. Faced with that pretty grim reality, the typical RC enthusiast's first instinct is usually solve a material weakness. Ditch that flimsy ABS A1 piece, replace it with something strong, like CNC machined aluminum.
Yeah.
Metal stronger, right? Problem solved.
That's the logical first step, yeah. And it leads you straight into, well, a critical dead end, frankly. We really need to put out a strong warning here for listeners. A direct bolt-on aluminum replacement for the specific A1 chassis brace, that's Tamiya part number 000 South 340, the one used on the Grasshopper II, and Super Hornet, it's just not commercially available from the main aftermarket guys like Hot Racing or Yacht Racing.
Okay, so what do people do? They find the closest thing online and try to make it fit.
Exactly. And that's the really risky move we need to steer people away from. Lots of folks try to retrofit the Hot Racing TGH 080801 part. Now, that is an aluminum brace, but it's designed for the much older first-generation Grasshopper and Hornet chassis. Those use a different A1 part entirely, number 0005164. It looks similar, but it's not the same.
And what are the actual dangers of forcing that older aluminum part onto the Grasshopper II chassis? What goes wrong?
Two major problems. Showstoppers, really. First, it's the incorrect width. The older TGH 0801 is actually narrower than the stock Grasshopper II plastic A1. So right away, it doesn't provide the proper cross chassis bracing it's supposed to. The tub can flex more. But the second issue, that's the real killer. Structural risks.
Okay, explain that. How can adding stronger aluminum be riskier than the weak plastic it replaces? That sounds backwards.
Because the aluminum part won't flex at all. So instead of the brace flexing open slightly and letting the arm pop out harmlessly like the plastic does, the rigid aluminum transfers all of the impact force directly into the mounting points. Those three little holes in the main plastic chassis tub where the tapping screws go in, the plastic A1 fails sort of gracefully. The aluminum forces the expensive main chassis to take the hit.
Ah, I see.
Instead of just bending and letting the arm dislodge, the impact force gets concentrated by that rigid aluminum piece acting like a wedge. This massively increases the risk of either stripping the threads right out of the plastic tub or, much worse, actually cracking the main ABS chassis tub right around those screw holes. So you've turned a cheap, easily fixed momentary failure, popping an arm back in, and into a potential catastrophic permanent failure of the entire chassis. Game over for that tub.
Wow. Okay. So the direct reinforcement path is either impossible because the part doesn't exist, or it's actually dangerous and leads to a much worse failure mode. So what does this all mean for someone wanting a tough, reliable basher? Sounds like the only real solution has to tackle the whole flood system, root and branch, which brings us to the big upgrade. The double wishbone suspension conversion. But hang on, I have to ask the skeptical question here. We just spent a good chunk of time talking about how weak plastic leads to catastrophic failure. Now you're telling me the best solution, the definitive fix for aggressive maximum durability bashing is made of plastic again. Something potentially 3D printed on maybe a hobbyist machine, not even a factory part. That feels really counterintuitive if you want long-term survival.
That's a totally fair question. And the skepticism is understandable. But the critical difference here is twofold. Geometry and material science. We are absolutely not talking about the same kind of weak, stock ABS plastic or, cheap consumer-grade PLA filament you might print at home. We're talking about engineering-grade materials combined with a vastly superior geometric design.
Okay, break that down. First, the geometry advantage.
Right. The double wishbone setup, it uses two arms, an upper and a lower control arm, to hold the wheel hub, the knuckle. This arrangement gives designers, basically complete control over how that wheel moves throughout the suspension travel. It means you can design it to virtually eliminate both the terrible bump steer and that tragic camber gain we talked about earlier.
Which immediately makes it drive better, more stable, more grip.
Absolutely. A night and day difference. The buggy tracks straight over bumps. It keeps the tire flatter on the ground for way more cornering grip, and it's just far, far more stable and predictable, especially at speed. You're not fighting the car anymore. And crucially, this whole conversion abandons the original failure-prone A1 retainer and the A5-A6 pivot nub system entirely. It just throws it out.
Okay, so the design is fundamentally better.
Yeah.
But what about the materials? Why is a 3D printed solution the recommendation here for durability?
Because the RC enthusiast community, guys who are really smart engineers themselves, have leveraged modern additive manufacturing 3D printing, but using materials that significantly outperform that original Tamiya plastic in both strength and impact resistance. When you look at designers like Ampro Engineering, who are widely seen as leaders here, they offer these comprehensive conversion kits. They replace the stock lower arm, the upright or knuckle, and add an upper link mount.
And what are these parts made of?
Typically, you'd order these parts through industrial 3D printing services like Shapeways, for example, and you'd specify advanced materials. Nylon 12 or TA12 is a very common choice. Now, unlike basic hobbyist plastics, nylon 12 is a proper engineering-grade polymer. It's known for excellent tensile strength, really good flexibility, which helps absorb impacts, and just superior overall toughness and impact resistance, exactly what you need for bashing. And these kits, they use modern, robust mounting methods too, usually steel hinge pins captured inside heavy-duty printed hinge pin blocks. There's absolutely no way for the old pivot nubs to pop out because, well, they don't exist anymore in this system.
Okay, that makes perfect sense now. So the innovation isn't just the better geometry, it's also having access to these high-performance materials that let you actually execute that better design reliably. It's moving way beyond the limits of that 1980s ABS.
Precisely. Yes, it's a bit more involved to install than just swapping one part. Medium complexity, maybe? But the payoff is huge. You get a front end that is both structurally sound and performs like a modern RC car.
Right, so let's summarize the choice for you, the listener, especially if your main goal is maximum durability and performance for really aggressive bashing use.
Yeah, given that goal bashing and considering the real dangers of trying that aluminum retrofit onto the flawed stock setup, the recommendation has to be pretty clear-cut. The double wishbone conversion is, I'd say, the only truly viable path forward. It fundamentally transforms the vehicle, it takes a vintage chassis with some pretty serious mechanical flaws, and elevates its capability, making it genuinely competitive in terms of modern performance and toughness. It solves both material and the geometric problems in one go.
Fantastic. That's a really clear path forward. This deep dive really hammered home that sometimes the most obvious direct fix isn't the right one at all. Simply reinforcing one weak component can counterintuitively just shift the failure point somewhere else, maybe somewhere even more critical, turning a small problem into a total disaster.
Absolutely. And it really highlights a core lesson in engineering and maybe even restoration sometimes. The most effective solutions often require you to completely discard the original flawed foundation and build something new upon it. It's pretty amazing, actually, how modern materials, science, and pure enthusiast innovation, spurred on by accessible tech like industrial-grade 3D printing, are really changing the game. It lets us take vintage designs we love and truly elevate them to meet modern performance expectations.
A great point to end on. We'll catch you next time for another deep dive.